Okay, so welcome everyone. Today we have the pleasure to have Michael Högele, and he's going to talk about large deviations for light-tail Lévy bridges on short time scales. So Michael, the floor is yours.
So first of all, thank you very much for the very nice invitation. So I thought also Renato could be here, but he had a health issue, so he could not. But thank you very much for the very nice invitation. I'm going to talk about several things. So a very short overview over my talk here. The first part will be rather elementary because I was told that there are students in the audience who are not familiar with Lévy processes. Not so much about LDPs because I'm going to talk about this a bit later. And then I'm going to talk about the motivation of our results and why we need these kinds of large deviation principles, how we obtain them, and this will be via certain fine estimates of a certain compound Poisson process. And in the end, just gathering all these things into an LDP and the statement of the full-blown statement of our LDP result. So the first part will be rather elementary, for those who already know. The question is, what is a Lévy process? And the first thing you have to take into account is, where I hope that most students can follow, you start with binomials, and you can recenter binomials, they can renormalize, and if you do this, the binomials, sorry for the quality, this is before the AI. If you recenter and renormalize the binomials, they become more and more Gaussians, and in the end, you have Gaussians. And you can do this not only for the final distribution of the sum, but you can also look at sub-partitions of these sums, and you still have these kind of convergence to normals. These normals, random variables are the sums of Bernoullis, and these Bernoullis are IID, so you can just split them up wherever you want. And if you do this, what you get up is something which is normal, and you can even do this on a larger scale with a lot of subdivisions, and each of the parts behaves has its own central limit theorem. And in the end, what you get up with is some kind of limit which is supported on continuous functions which start in 0, and you have a lot of central limit theorems all in between, and they're all independent, so you have independent increments, and this is the so-called Wiener measure. This is one way to introduce Brownian motion. It's rather swift because you have to be acquainted with the central limit theorem and possible extensions, but you can also start bit different. You could also start with Brownian motion being a stochastic process who has continuous paths. They start in 0, and you have that whenever you pick n points in time, the increments, the random increments, are all independent. And you can always shift them to the very beginning. This means if you have bt minus bs, this is the same as bts minus b of 0, but b of 0 is 0, so we have just this here, and this should be normally distributed because we had this central limit theorem behind there. Well, and this has a certain representation. This is maybe, if you're not familiar with this, it's not so important. It's just you can write this as a certain power of this kind of distribution. So this is a certain process. These are random functions which have this kind of behavior, and families of random variables which have some kind of properties. These are the first class of processes when you look at Lévy processes which are interesting. The next class of processes which you can have a look at are much, much simpler than Brownian motion. Brownian motion is, so to say, a classical case, and it's a very particular case in the realm of the Lévy process, because typically Lévy process will turn out to have a discontinuous path, while Brownian motion has continuous paths. So if you think of a Poisson process, well, the definition of a Poisson process, how can you define it? You have a sequence of exponentially distributed, this means memoryless waiting times, all IID, and you wait the first one, and you add +1, and you wait the second one independently of the first one, and you add +1, etc. And if you do this, well, you know many things about this. For instance, at the point t, it's a Poisson distributed random variable, which has the intensity lambda t. So lambda being just some kind of parameter, being the parameter of the waiting times. And you can calculate the characteristic function, and you can ask yourself, why would you do this? The point is, in the end, here we can still calculate things, but a bit just 2 pages on, we can not anymore calculate anything. We can calculate, for instance, the characteristic functions. So characteristic functions are very important because they characterize the laws. And if you do this, you just write down what you have. You have e to the IU pt, pt being just the variable, and you have the values of the Poisson from 0 to infinity. You weight each of these e to the IUs with the respective Poisson probability, and then you have an exponential series. And if you calculate this, just joining these two terms, the n's and the power here, you get the expectation of t lambda e IU minus 1. Okay, so this is very interesting. What are the properties? Well, they turn out to be rather similar to the one of Brownian motion, well, except for obvious differences. You start at 0, you still have independent increments, and the increments are stationary. Once again, you can just shift any kind of increment between one point in time and another one to the very beginning from 0 till the difference of these points, because once again you start in 0. And you can write down then the distribution. This is a Poisson distribution with the parameter lambda times t minus s. And once again, you can write this down as some kind of convolution power if you would like to. Well, then you can extend this. So what did we do in the Poisson case? In the Poisson case, we waited at the waiting times, and then we added just ones. If you replace these plus ones by another IID sequence with some random vectors, maybe in RD, or which have a certain distribution, then you get the following picture. You have tau1, then you have an increment of this W1. Maybe it's a random height now, independent of everything. Then you wait a second time, you have another one, and so on. And this is the formal definition. You have a Poisson process, which gives the times when the jumps occur, and the waiting times, so the times between the different jumps, which are once again independent, and the increments which you sum up as such. Well, here in general, you don't have better things than just a characteristic function. Of course, if you like power series, you still have something at hand. Nevertheless, this is a convenient way to represent the laws of these kind of compound Poisson processes in a way which includes the original parameters. You have e to the minus t. You have here the jump distribution, which is not normalized here. So you can also divide, if this is finite, divide by the lambda of RD, multiply with lambda of RD, then you have just something which is some kind of expectation once again. And we can calculate this. Well, if you do this, we have e to the IU, and you have compound Poisson process. What is this? This is the sum from 1 till pt, pt being this independent Poisson process. You have these increments here. And the interesting thing is that if we just disintegrate, so we can just fix a value of pt times the probability. So we have the, here's the probability of p here is to close this pt. What we have is we have a conditional expectation here, conditional to the event of pt being k. And but the wi's are independent, so you can just replace the pt by k. And what you get here is something e to the IU, and then you have a sum of things in the exponent. And if you do this, what you can see is this is just because of the exponential structure, a product of independent things. And this is uncorrelated. You can just separate this. And you know very well the distribution of the Poisson process. So we have the distribution of the Poisson process, and here we have just the first characteristic function of the first increment to the power k. Once again, you can just join these two things, the power k's, and what you get here is an expression which is an exponential, because we have here this exponential series. We have e to the minus lambda k, which is just this what happens here. And we have an integral with respect to the unnormalized distribution of the wi's. Okay, in the case of having just the plus ones, which are just a Dirac measure in one, we can just recover the original formula, and this is what we get. So we can have something, we can say something about these things. They have a very interesting structure in the characteristic function. We have the unnormalized distribution of the increments and the intensity of the jumps. So what are the properties? Well, they are once again close to the ones of the Poisson process. Once again, we start in 0 with independent increments for any n which we might choose, and any kind of growing sequence from t1 until tn. And once again, we can just shift the increments all to the very beginning. In comparison to the Poisson process, I will just flip back. Please forgive me if I flip back here. Here we had the Poisson distribution, right? In the compound Poisson case, where we have these increments which are not +1, well, these are a proper class of distributions, and in general, we cannot say anything about the densities in an elementary way. These are just power series in terms of the inverse of the characteristic function, if you want so. But this is a complicated structure. So, and these building blocks, Brown in motion and the compound Poisson process together, are the essential parts of Lévy processes. What is a Lévy process? Well, a Lévy process is a process who starts at 0. Here's independent increments and stationary increments in this sense. You can just shift the increments once again to the left. But we have to pay a price. Exactly like for the compound Poisson part, we have to take into account that we don't have continuous paths, we have right continuous paths with left limits. So these are cut-like functions. And so how does the characteristic function of such a Lévy process look like? Well, it should contain a component which contains the Brown in motion part, which contains the compound Poisson processes. And then maybe, okay, linear functions. Linear functions just comply with everything. Linear functions starting at 0, okay, it's deterministic, so all these things are satisfied. And then we can see that we have essentially these 3 parts. Well, we have 4 parts, essentially. We have here the linear function. So if you look at the characteristic function, we have the characteristic function in 1 to the power t, and this is e to the t times, and then we have something which is the characteristic function of the Lévy process at time 1. We can always do this kind of shift in time due to the stationarity of the increments. And if you do this, here we have the characteristic exponent of a linear function. Here we have the characteristic function of a Brown in motion. Here we have a characteristic function of a compound Poisson process, which has jumps which are larger than 1, and then we have something additional which are just small jumps. And small jumps, they can be very heavy, and this is reflected in the case that the measure which appears here, the unnormalized increment measure, for large jumps has to be finite, while for small jumps it is not necessarily finite, but can have even an infinity. It can have a pole in 0. This means we have an integrability condition, which just gives us y squared dy integrated is finite. So this y squared is small. It tends to 0 for values which are smaller and smaller. This means we can allow for even a pole close to nu, and this is something which happens quite a lot. This means there is no finite measure to represent the intensity, the frequency of the small jumps. More or less, it says that smaller and smaller jumps can be more and more frequent in a very controlled way, because we still want that this is finite and this is a squared here. It's not no arbitrary power. It's a very particular structure. So we have 4 building blocks: a linear, well, the characteristic function of a linear function, of a Brown in motion, of a compound Poisson process, and many small jumps, so to say. And these are in the exponent. and they're additive. This means in the exponent being additive means that they become independent. Okay, this is on the level of the laws, right? So distribution of the Lévy process at time t. You can do this even on the level of processes, which is much, much stronger. So if you have a Lévy process, you can really filter out different kind of components. You have a linear function, you have a Brownian motion, which does not need to be a standard Brownian motion, but can be distorted by some kind of covariance matrix. And then we have compound Poisson process. This infinity is for large. And we have small jumps, small and bounded jumps. Okay, so this is more or less the classical theory. What you need to know, and basically, if you first encounter Lévy processes are quite common. They are, so to say, the integrated noises in some sense. We have always stationary and independent increments, and this is one of the most natural models. Well, here are some illustrations. If you have a pure jump process, it can look like this. We have maybe a lot of small jumps, and from time to time, because this is a compound Poisson process where we have waiting times which are not essentially very, very small. They can be just being finite. From time to time, we have larger jumps which correspond to the compound Poisson process. And in comparison to the Brownian motion, we can just look at pure jump process versus Brownian motion. Brownian motion has continuous paths, and it is much more rigid. It has a much more rigid structure because it's a Gaussian increments, and there's a lot of Gaussianity in there, which means relatively few parameters in comparison to Lévy processes, which are always parameterized by some measure, and measures are infinite dimensional things. Right? So in comparison, Gaussians have these covariance structures, which is just a finite dimensional object, while the Lévy processes are much richer, especially in the case where we have poles close to zero. In addition, due to the Gaussianity, all moments, including some exponential ones, are finite. If we go over to Lévy processes, first of all, we don't have a closed density. We know something about the characteristic function. The paths are typically discontinuous, and they're only Cutlack, they're continuous from the right. And moments, if you have small jumps, then we have exponential moments. If we have also compound Poisson large jumps, there can be very few moments. There can be even as less as moments as you would like. Okay, so far, this is what I wanted to say about Lévy processes. Are there immediate questions from the students in the audience, maybe? I just wait this in order to see.
Seems there are no questions, I think.
Okay, so from time to time, I will ask for questions and come back to this. Okay, so you tell me. Thank you. All right, so what I'm going to talk about. I'm going to talk about, I would like in the end to come to a very strange LLDP, large deviation principle, for objects which are also not the most common ones. In particular, there are LDPs for Lévy bridges. This means Lévy processes conditioned to end up in a certain point. These kind of objects, they don't seem to be natural in the first place. And I want to motivate them where they originally come from. The first thing is, so the first much more natural motivations are first exit times for SDEs. If you have a stochastic differential equation, this means you have essentially an ODE perturbed by some kind of Brownian motion, where you have a small prefactor epsilon starting in some point. And you ask yourself, what is the first time that you leave a certain interval? Okay, once again, sorry, I had to close the brackets here. The first time that you leave a certain interval minus AB. And then this is a very, very classical question. It has precursive results even in the 19th century. And on a rigid level, it was treated for the first time by Friedrich Wenzel, and then onward from the 1970s, 80s, 90s on, there was a huge literature in exploration of all these stuff. Also, people from IMPA and many other places were involved. And what you have is that the expected first exit times, they behave like e to the, and then you have some kind of function which depends on a certain potential, pseudo potential, evaluated in the highest point you have to overcome, divided by epsilon squared. So this is e to the constant over epsilon squared. So this grows very much. This means for epsilon tending to 0, the process likes to leave very little. So the times grow very, very fast. Well, so I don't want to go into literature. It's just too big. So I don't know where to start. So this was for a long time a main issue, and it has a lot of sophistication there, even for degenerate use. You have multiplicative noise, you have many things. And maybe I should say something about this. This theory relies on large deviation principles. This means Schilder's theorem. This is a large deviation principle for Brownian paths. And this has, if you have some kind of push forward of this kind of flow, then you can apply as a continuous push forward. Then you can apply the original LDP, and then you get a new LDP under this push forward, which might be, for instance, a solution of something like this. Even in a situation where this structure does not hold anymore, it can be extended considerably. Okay, at the beginning of the 2000s, my PhD advisor, this was Peter Högele, and others, they started to look at first exit times for other types of processes, for alpha-stable processes. So these are Lévy processes, which are not, so the drivers are not here, the Wiener process or Brownian motion, but the drivers are alpha-stable processes, which have large jumps. This means we have a Lévy measure which has decay, and the decay is a very characteristic decay. It's something like 1 over dy to the alpha plus 1. So we have something which decays very with very heavy tails. And what you get is you can also characterize the expected first exit times, and they behave very differently. So there is no exponential growth, but the growth is like 1 over epsilon to the alpha. So this is something which is on a very different type of time scale. And in comparison to, for instance, the Brownian motion, here you can see very clearly the difference, the influence of the potential. In other situations, this can be a bit more indirect by a quasi-potential. Nevertheless, you can see that the potential really is something which determines. Okay, this is a P here. So I'm sorry. Nevertheless, you can see that there's a very strong influence of the potential U to leave in the exit times. If you do this for the alpha-stable process, you don't get this. You get more or less a dependence, which is, instead of a height of a potential you have to overcome, it's something which is much more horizontal, and you can interpret it as just the measure of nu of the complement of AB. This has to do with certain properties of these measures nu. They have a certain scaling property, and from this we can derive these kind of behavior. It's very different kind of behavior because we have the presence of large jumps. These jumps are heavy-tailed, and they are rather infrequent. So they have to wait. Well, no, let's say they're frequent in the sense that the excursion of small jumps take much, much longer than the interruption by a large jump. What does it mean? This means exit events are something like you're starting somewhere, then you move close to a certain minimum, a local minimum, and then you're perturbed, and then from time to time there's a big jump who tries to kick you out of the interval, and then if you don't exit, you just come back, and you remain there for quite some time. And you do this back and forth, and what you get essentially is some kind of a geometric sum. So we have no, 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 until yes, the first exit, which happens by some large jump. Okay, these are the results which are obtained there. There have also been quite some sophistications since then. The first results were for additive noise in one dimension, then several dimension multiplicative noise. My PhD thesis was about applications for this in some SPD case, but we also did something, for instance, with delay equations where you have very interesting dynamical features coming up. All right, so this is these are perturbations with alpha stable noise. And then some years later, well, you can see, you can see that the alpha stable and the Brown in motion case, they behave very differently. You can interpret an alpha stable process with alpha equal to 2 as a version of Brown in motion. So one would expect, or one could expect, that there is maybe something, some kind of continuity even for the exit times. And this was one of the questions a PhD student of Peter Högele had to work on, and this was Thorsten Wetzel. I'm going to talk about him a bit later. And he looked for Lévy measures which have these kind of densities. So they are, in some sense, lighter tails than any kind of polynomial tails. But according to the, so these are e to the minus. Here we have some norm of y to the alpha between 0 and 1 at first. So this is heavier than purely exponential. Purely exponential would be equal to 1. So there's still some kind of sub-exponential tails. And in this case, you have essentially the kind of behavior you would like to expect. So we have something which grows like e to the constant over epsilon to the alpha. Well, this is something you would expect. But then something unexpected happens. If you cross alpha from 0, 1 to 1, 2, things behave quite differently. So this means you have jump processes, and these jump processes have lighter tails than exponential. And there can even be Gaussian increments. So this for alpha equal to 2, doesn't matter, or even bigger, even lighter. But it doesn't change the picture. What happens there is you suddenly don't have e to the alpha here, but you have something like epsilon, so to the 1, and then you have some kind of correction which appears. This correction has to do with the quantile, and it's rather different. So in their papers, in the analysis of probabilities, they just put up the whole scale of different exit times. And these kind of results were obtained by looking at the compound Poisson case for a fixed number of increments. And Thorsten then solved several optimization problems. For alpha between 0 and 1, these optimization problems are essentially concave. And for alpha greater than 1, they just become convex. And this becomes a very different kind of structure. This means the optima are first at the boundary, and suddenly the optima are just found somewhere inside which you have to calculate. And this is what happens there. It's a very different kind of structure. Just some words about Thorsten Wetzel, my co-author here. Thorsten he was a PhD student by Peter Högele, but he was not a normal PhD student. He was always working in the meantime. He's a professor at a public school in Germany, in Berlin. And he has these kind of projects as his personal side projects. And he published, so he and Peter Högele and Ilya Pavlukevich published with him these results, and was his diploma thesis.
I have a question. I'm a bit surprised that you don't have a dependence in. I would expect that in the limit you would get something that depends on also on the max of modulo A and B in absolute value.
Oh, okay. Well, thank you for the question. So you're talking about the exponential or sub-exponential case, or the alpha stable case?
Sub-exponential case, yes.
well, in the well, let me come to this. Just one moment. Okay, it's just you get something which is which has to do with it, but not as directly as you think. It's a second order where this U dependence appears. Okay, so this is yeah, very interesting. So thank you very much for the question. Just keep it, save it, and I'll come back to it. Okay, so Thorsten, he wrote this, and this was his diploma thesis. So this is quite remarkable from my point of view. And some years later, he asked, he handed in his PhD thesis, and this was in 2022. And what he found out is that the exit times are always dominated just by the side of where you will exit. So you will the noise determines essentially where to get, and you get something in terms of and here you're right, in terms of the distance from zero of A and B. So this is what determines the exit direction. So if you restrict yourself to symmetric Lévy measures, his motivation was he wants to refine his results he obtained here, until in the first exit results you can see the influence of the potential, because here you cannot. So everything is determined essentially by the noise. And the result he got out, what is that in the case that you have a symmetric noise, you can determine the direction where the exit happens, and here you can see that the potential plays a role. There's a new term appearing, and in this new term, in fact has so to say the exponent of the potential which appears, of the derivative of the potential which appears. So it's a rather deep and complicated result. And in order to prove this, he had to prove an LDP. So these are pages and pages of calculations. And in order to obtain this kind of result, he used a generalized LDP for Lévy bridges for, first of all, Lévy process of this type. So first of all, coming back to your question, does this answer somehow your concern?
I'm not sure. This is about super exponential, right? My question was about the sub-exponential case.
Oh, the sub-exponential. No, in this. Oh, I'm sorry, I didn't. Okay, in the sub-exponential case, on this level,
the limit is 1. I would have expected a limit that depends on the distance.
Oh yes, okay. Okay. This limit here depends on essentially on the measure. This depends on the measure. And okay, and on B, and A and B. This is correct. So the measure has some kind of norm here. This is you're right. Here is a factor missing. This factor missing here depends on A and B, but it does not depend on U.
It depends on where the minimum of U is, right? The minimum is at 0.
Yes, exactly. This is at 0.
Okay.
Yes, exactly. So it's a distance from the point. Yes, exactly.
Thank you.
Oh, sorry, Michael,
Okay.
can you go back to the previous slide?
Which one? This one or this one here?
The previous one. So also there, so you have that factor, the Lévy measure of the complement of AB minus AB.
Yeah.
It's the okay, thanks.
Yes, exactly.
Okay.
So, okay. So, and coming to this point, this is the reason why generalized LDPs for Lévy bridges are important. They come here in order to prove results for first exit times, finer results for first exit times in super exponential cases and in higher dimensions. Okay, so you would not know where they come from, and these are the reasons. Okay, so he showed this in his PhD thesis in
We lost the audio, right?
Yeah.
Ah, okay. I'm right in the chat.
There is a green arrow, perhaps he's trying to enter. I don't know.
Having a look at this, it's not unnatural that these kind of things could happen. Okay.
Mike, sorry, I
Please.
think there was some technical issues.
Can
Is
you?
me? Yeah, I cannot see your screen anymore, and I could not hear you for.
Okay. So I'm trying to. Okay. Can you see me now? Can you see the screen now? Okay.
Me, no. Also, yeah.
Am I sharing?
Okay, now I can see you, but I cannot see the
Okay.
shares.
I'll share again. Thank you.
Mhm.
So I'm going back. Is it better?
Yeah. Now, yeah. Thanks.
Okay. Please, just at the first moment, I'm disconnected. Thank you very much. Okay. So I want to say that these things are these results depend on LDPs for Lévy bridges on generalized LDPs. This means we have some speed functions which may be not just epsilon itself. Okay. For this, we also need a regularly varying function, and even a bit more than this smoothly regularly varying function, which are just a subclass of the regularly varying function. You can think of those who are C infinity and their derivatives behave as essentially as the derivatives of power functions. This is essentially what we want to have here. We need this at certain points. I'll show you. And this is how these kind of smoothly regularly varying function behave. There are also well-known objects in the literature, but nevertheless, not everybody is familiar with this. In particular, you have that lambda times f prime behaves essentially like f itself up to the power which comes here. This means if you have a power function, you have just equality here. And for a smoothly regularly varying function, you need this kind of behavior asymptotically, right? So if you look at the LDP for these kind of Weibull type processes, I'm going to talk first on all the proofs. Or the sketches of the proofs I'm going to show. There are compound Poisson processes. You can always think of intensity 1. And they have a Lévy measure which has this kind of density. It is e to the minus f, f being smoothly regularly varying with index alpha, alpha greater than 1 of the norm. So this is also rotational invariant and has a certain decay. Okay, so we are here in Rn and we are rotationally invariant for each single jump. So then we need then we fix an endpoint, we fix an end time, and then we look at our Lévy process, which we renormalize in a certain way. We have a prefactor epsilon here. We have also a stretching of the time. This stretching of the time can be larger or smaller as this e to the something, and the something can be with positive or negative exponent. I will show you. And then we have the segment between 0, so the n-dimensional segment between 0 and the end time, And then we look at certain paths. These are all paths in between 0 and t, and the Cutlack in the space of the Goddard space between 0 and t, which start in 0 and which end up in x bar. And they are non-decreasing in this one direction. Okay, so this is what you have here is that they are invariant. And what you get is that if we then look at this kind of process and we condition this renormalized Lévy process to reach an endpoint at the end time, This means we have a compound Poisson bridge. Then this compound Poisson bridge satisfies a generalized LDP. We have a certain speed function. This speed function is epsilon times, and then there appears something strange here. This is a g. This is a function which is still not known. This g is the solution of a nonlinear functional equation, which you have to solve. Here we have r epsilon, and we have a good rate function, which is essentially, looks a bit like some kind of energy. So this is the integral from 0 to t. And then we have here the derivative of the absolute value of phi times the logarithm of this phi prime minus the end value, so the absolute value of x bar logarithm of x bar over t. If we are in these kind of paths, so this is for very, very narrow paths, for a very, very narrow class of function. These are essentially perturbations of the straight line. So the straight line is just the straight line parameterizing on 0 t 0 till x bar is the minimizer, and all function which leave these this segment, they have the intensity infinity. So this means the only paths which are not degenerate are those who are living inside this parameterizations of 0 until x bar. Okay, so this is the result which we have there, and this is necessary in order to prove these kind of first exit results, which are advertised just before. Okay, so first of all, the most important thing is the statement. Please, I welcome any kind of questions about the statement I'm giving here.
Yes, can you hear me?
Yes, yes, very good.
Yes, so perhaps not about the statement, but like this infinite showing up is perhaps kind of surprising at first hand. So is there kind of a simple explanation why reaching x in some, well, not staying exactly on the segment is much more costly than making a deviation just by changing the way you increase the modulus?
Absolutely, yes, of course. The reasons are the properties. So if I may, let me see. No, just give me 3 slides and I will come directly to your question, okay? Because we have to solve this kind of functional equation G here, and this is a certain property, a certain cancellation property. And you can see that if you are inside this, in this segment, the cancellation property just gives you different kind of terms, which just removes the blow up. While once you're outside, you have an incomplete cancellation and you suddenly have this kind of blow up.
Perhaps a question related more to the statement. So this statement is for you have alpha between 1 and 2 strictly.
No, no, it's just
just alpha larger than 1.
Yes, exactly.
Okay, so it doesn't alpha larger than 2 doesn't change anything. Okay. Okay.
Not at all. Not at all. So Gaussian increments are perfectly fine. Or Gaussian type increment. Yeah. Okay. So once again, so for instance, exactly. So we can think of Gaussian increments here, and they're perfectly okay. So everything relies on good upper and lower bounds for the densities of the compound Poisson process. So estimates for the compound Poisson process, and this is an extension of the work Thorsten has been doing in the simpler case, in the one-dimensional case I was talking before. And what you get is you have that the density, well, here we are talking about the exponent, so we have the logarithm of the density has an upper and lower bound for large values of x. So x is the variable, we're looking at, and we have very fine estimates of the same kind of type. And these kind of estimates, they have a main term. This is f prime g of the norm of x over t. So we can even see the dependence on time here, which is typically, you have to be very close in order to see these kind of asymptotics. And you have a lower order error term, which is just g itself. Okay, now the question is, who is g? And g is the unique solution of a certain functional equation. Well, just remember, f was something like the power of alpha. So this is something like a polynomial alpha. So you're searching for a function, g. F is given such that if you plug it inside a kind of polynomial, you multiply with g. Then you just subtract f of g. And then you add the logarithm of g, and then you have some logarithm of the second derivative of g is something logarithmic. Well, this is, of course, undigestible. So when I saw this first, I was more than puzzled. This is why let's have a look at a bit simpler case in order to have a clearer feeling what this is. If we look at the density of just this kind of type with the power function, it looks like this. Here we have the f and the f primes all removed, and you can just write the different powers which we have here for the estimate. And the g is a function which satisfies that g to the alpha plus the logarithm of g is something like the logarithm. This means you can expect that g is essentially something. So this term is, of course, of much lower order because it's the logarithm of g. So you can expect that g is something essentially like the logarithm of lambda to the power 1 over alpha in order to cancel, to have this. Okay, so this is essentially the order which you can expect, and this is what is written down here. It is some kind of power 1 over alpha of the logarithm. And if you take it to the power, so g to the e to the something, then you get something of a smoothly regular function of 1 over alpha. So if you accelerate this once again, then you get the power. So if you remove the logarithm inside, you get this. So okay, so you get upper and lower bounds for the density, for the exponent of the densities in terms of the f's and the g's. Okay, so the question is, okay, first, how could you solve this? And the point is, we only have to solve this asymptotically. And asymptotically, it's not so hard to see that you can solve this if you just think about some kind of deviations close to the logarithm to the 1 over alpha. So it's not so hard that this has a solution. But it has a lot of interesting and important properties. And the important property is, of course, the property in red. And this is just the answer to your question. The solution of these kind of equations has a certain cancellation property. And it looks like this. So g, and then we have the difference of f prime g of y lambda minus f prime g of lambda behaves like the logarithm, and this is just logarithm itself is of lower order because delta can be arbitrarily small. So what you have here is something which allows you to have a controlled cancellation of certain terms, and one of those terms is the term who creates the blow up in a Riemann sum. So if you will have a look at it maybe in 5 to 10 minutes, where these kind of sums appear, and if you are on the segment, this kind of cancellation will just remove the bad part, and in case you're off it, you have the blow up. Okay, I know this is preliminary, the answer, but I hope this gives you an idea where things come from. Is it okay?
Yes, thank you.
Okay, so you have to solve a certain nonlinear functional equation, and the solution has this kind of property. And this property just determines this very particular shape. So how would you prove this? Well, first of all, you have to see that the density of the Poisson process is nothing but the decomposition in terms of the jumps. And in order to have this, we have the probability of the Poisson process, and then we have the density of the nth power convolution of the Poisson process with itself. So this is for nu, we can think of that we have intensity 1. So this means the nu itself is a probability measure. Okay, so everything boils down in this formula to knowing the nth power convolution. And in order to do this, we get an estimate which is essentially sharp on these times of scale we are looking at. And here for these kind of estimates, so just to say something about the mu, in the estimate of the nth power convolution, the G does not appear. It appears coming back to the density itself. Okay, so for this, for the factor m, we don't need it, not yet. So here we have an estimate. This estimate is a rather technical estimate, but nevertheless, it has it's ingenious how Thorsten just solved these kind of problems. So first of all, you can write down the convolution. So this has a density which is very well known. So this is just writing down the convolution as itself. And then what you do is you rewrite it and you introduce an additional function f sub xm. Okay, m is the number of steps you have, and x is the point of the density. Okay, so if you do this, you can see that essentially we need estimates on these kinds of functions f, and in order to have those, we use that that f is of this smoothly regularly varying type. So this is something which you have to take into account, which we have there. So I see that my time is limited to 5 minutes, something like this. Is it correct?
Yes.
Okay, so then I will just go on a bit, and you can see that we have essentially, we can write it as in two terms. Each of the terms can be estimated in terms of the second derivative. The second derivative is nice because here we have squares appearing, and then we can use, done properly, we can use the Gaussian renormalization. So this is the trick. You compare first order approximations with the second order, and what you get is our Gaussian approximations. All right, so I will skip this here. For the lower bound, we can do similar things. It's quite ingenious changes of variables which appear here. In the end, I want to come to maybe the next slides. We want to show the lower bounds of the density, at least to have a rarity where this nonlinear functional equation appears. Okay, so in fact, you don't solve this functional equation itself. You solve an approximate equation of this. Okay, I'm sorry for this technicism. Nevertheless, if you do this and you choose a certain parameter of your sum, you don't take all of it, but you're a very well chosen one in terms of the solution which you have here. And then you can just estimate it by one of those sums, and then you have to calculate and to use the bound you get for the nth convolution, of nu for this kind of parameter. Okay, so the parameter is very well chosen. So it is essentially a function of x, t, and this function g here. And if you do this, you can see that all these terms which appear here, they are terms which appear in the functional equations. So if you have this kind of properties, so you can see that this kind of estimates are all, you can see this n half here, you have f of g, you have the logarithm of g. You can see all these, for example, you swap them by the terms which appear in the functional equation. So you have this equation in order to replace several terms here. And in order to get this, you have to use that the function g naught, which you solve here, is close to the original function equation, which is a bit simpler. Okay, so this is the main point here. Going from this line to the next one, you just swap the terms which appear in the functional equation by the correct ones which you have here, and then we have essentially the bounds. Okay, so this is the main idea which we use. Okay, then we can write down this was the estimate for the Compan-Poisson process, and then we can write down the heuristics for the LDP. So if you do this, so we have here the densities. The densities of the bridge are very well known. So okay, you go forward and to the middle and then to the end, and then you have to normalize to having gone the whole interval. And okay, and then you can, if you do this in just one intermediate step, you can see that these terms just appear here. Okay, and in order to do this, we have to distinguish being on the segment and off the segment. This is which will come here. And if you do this, then we can see that these kind of differences in the Riemann sums, and these differences in the Riemann sums behave in a way which you can control. Okay. Okay. Of course, obviously, you can see that I cannot go into details here. If you're interested, I'm more than happy to send you the slides to go into this. But the idea is to go into the Riemann sums and to see that on the segments, the cancellation in fact happens. This is something which you have here. And if you are off the segment, so you have an incomplete cancellation, and then we have still terms which diverge. This means you can see that the limit goes to infinity. This is, okay, a very rough sketch here. In the end, I will more than happy to answer questions. I just want to write down the complete LDP which we have here. If we have some kind of Lévy process which is dominated by such a Compan-Poisson process, in the sense that you can write down, you can even add Brownian motion, you can add some kind of drift, and you can you have even smaller jumps which are substantially smaller than the densities of the original of the Compan-Poisson process. Then you get this kind of rate function equally as before. But you can just argue away all the parts which are not the Compan-Poisson part. Okay, so the lighter parts just vanish, and the only thing which is really determining the whole behavior is given by the Compan-Poisson process with this kind of super exponential tails. Well, and we have sufficient conditions that this is happening. Okay, there's an ORA condition. And there are even more things to it, but I think I should stop here, and I'm going to answer questions. Thank you very much.
Thank you very much, Michael. So are there more questions or comments?
So if you're considering other path, would you think you could have a different large deviation principle? I mean, like with a different speed and with a rate which is equal to 0 on this segment, but something non-trivial.
Thank you very much. Yes. So at the moment, what we're doing is to write down some kind of true Schilder theorem, in the sense that we have the segment, and then we have essentially a usual LDP for the other direction. So we have a different kind of scaling in the different directions. And we have the usual Schilder, movement in the orthogonal direction, and we have this kind of direction. It's a bit more difficult because you have to disentangle the different projections, but it's almost done. We're just there. This is the next thing we want to do. Thank you. Yes.
There more questions? No, I don't think so. Okay, so if that's not the case, let's thank Michael again.
No, thank you.
Thank you very much for the interesting talk, and we see next Wednesday. Thank you again, Michael.
Thank you.
Bye.
Ciao.
Ciao, ciao.